Hello, this is Jack Jackson. In this video and in this section of the notes, we start to introduce what is perhaps the most important thing in an entire course in probability and statistics, and that is a hypothesis test. Hypothesis tests are used to make decisions about a population by examining data from a sample so that we can make data-driven decisions. We will start this process by looking at what's called a one-sample z-test. So this section 4.4 has several subsections, so this will probably be around 8 videos or so. And you can see what we've got here. This one here will do the introduction to hypothesis testing. We'll follow this up with an example. So we're going to develop the theory first, the concept, and make sure that you understand that. Understanding the concept of a hypothesis test is very important. So in this video, we will introduce that basic idea, hypothesis testing. And after looking carefully at an example to develop basic concepts, we will then look at the classical test statistic method in video 4.4.2, followed by the p-value method in section 4.4.3. And we'll then work a series of examples, including a couple of two-tailed tests, a left-tailed test, and a right-tailed test. In section 4.4.8, we will look at built-in calculator shortcut programs for performing one-sample z-tests. So, here we go with our introduction to hypothesis testing. So the basic idea behind hypothesis testing is to use information about a sample to infer what is happening in a population without testing the entire population. And really, this is the central idea behind inferential statistics. Hypothesis testing is used to determine if the amount of difference between a statistic from an observed sample and either the corresponding assumed population parameter or another similar statistic from a different observed sample is likely to be due to inherent randomness of the distribution, or if it is more likely to be due to the observed sample being from a different distribution. That really describes what hypothesis testing is, but that's kind of a mouthful. So as we go through the next few slides, the next couple of videos, hopefully we'll make sense out of what that is saying right there. So hypothesis tests are among the most powerful tools for making quantifiable data-driven decisions. Again, hypothesis tests are the most important thing in this entire course. So here's basic overview. Suppose we find the mean of a sample and compare it to the mean of a known population. Well, we know there's always some variability. Even if the sample is representative of the population, the sample mean will likely be different from the mean of the known population. However, the sample mean will likely be somewhat close to the population mean of the distribution it is drawn from. Suppose the distribution of individuals is known in the known target population is normal. The sample means will vary naturally. The distribution of sample means is also normal with the same mean, but a smaller standard deviation. This is what we know from our work with sampling distributions. So we know there is variation in almost everything. Suppose there's a situation where there's a well-established history of some process with a known mean and standard deviation. Further, suppose that the distribution of individual values is normal. When we find the mean of a sample, we would expect it to be close to, but not the same as, the historical mean of the population. Now, suppose that we get a sample mean different from the hypothesized population mean. Well, there's two things that could be happening. The difference is because of the normal variation among means of samples drawn from this population, or the difference is because the sample is really from a different population with a different distribution. How can we decide which is the likely case? Answering this question is the main goal of hypothesis testing. So there are two causes of variation, or two types of causes of variation. So in other words, two possible differences possibilities for the differences or reasons for the differences in the means. One is what we call normal causes of variation. This differences of means is due just to random variation in the distribution of sample means. We know there's some variation no matter what. And if that's the only variation there is, then the sample is from the hypothesized target population. Now this is going to be likely if the differences in means is relatively small. We assume this is the case unless there is a preponderance of evidence suggesting otherwise. The difference in means, however, could be due to what we call special causes of variation. The differences mean there is due to something different about the sample. So the sample is actually not from the hypothesized target population. This is going to be likely if the differences in means is sufficiently large. We only assume this if there's a preponderance of evidence suggesting beyond a reasonable doubt that special causes are present. So some examples of normal causes of variation would be normal variation in weight changes from all people. Individual people have weights that go up and down. We have variations from person to person. Same way for normal variation of blood pressure of all people. And we have some normal variation in things that are manufactured, like diameters of pistons from variations in materials, methods, and machines. But we can also have special causes of variation. We might have a large weight loss from a group of people that are on an effective diet. Something other than just normal random fluctuation is at play there. Or there could be large drops in blood pressure from people using effective blood pressure medicine. We might have statistically smaller diameters of pistons from a broken or miscalibrated machine. If one of these things is happening, we want to know about it. So, for example, suppose we have a distribution of sample means, a distribution of x-bar values, say given by this normal distribution. Well, the center or sample, the population mean is right here in the middle. Say it's 101. But if we got a sample mean right in here pretty close to that, we'd say, well, that seems reasonable. That we would expect that to happen. That's probably the amount that it's off by being a little under 101. No, that's nothing to be surprised about. That's probably from a normal cause of variation. On the other hand, if we get something way out here, the probability we would get something way out here is so small that it's much more likely that that's probably from some special cause of variation. This value way out here, if we got a sample mean way out this way, or equally way out the other side, that would be something we'd say, hey, that's so unusual that that's probably because this is not really from this distribution. Something different is going on, like maybe the machine got broken. What about in here? Well, now it's a little harder to tell. Boy, it'd be nice if we had a number that it could help us measure if this was likely a special cause of variation or a normal cause of variation. And that's kind of where we're going for a hypothesis test. So hypothesis testing allows us to quantify what we mean by saying that the differences in means, or some other statistic, is sufficiently large enough to have a preponderance of evidence suggesting that special causes of variation are present, and the sample comes from a different population than the hypothesized target population. So hypothesis tests allow us to answer the question, how do we determine if the sample data provides enough evidence to say that the sample mean is sufficiently different from what we would expect under normal causes of variation, so that we can conclude that the sample is really from a different population? And if so, how can we quantify our level of certainty? What we basically do is assume that only normal causes of variation exist unless there is sufficiently strong evidence to suggest otherwise. If we're trying to prove something, we typically assume the opposite until we have strong enough evidence to suggest otherwise. The burden of proof is with the researcher. We start by having something we call a null hypothesis and an alternative hypothesis. The null hypothesis, H sub 0, is basically a status quo assumption, and that is that the distribution of the sample statistics has some known distribution. In our first several examples, the null hypothesis is that the distribution of sample means is normal with some specified, known, or at least assumed mean, mu sub 0, and standard deviation, sigma. The alternative hypothesis is basically what we're trying to prove. Now, one of the best things I can do to help explain this is to compare it to the American justice system. So this analogy works with the justice system or courtroom. So remember that one of the most basic tenets of the U.S. justice system is that the defendant is presumed innocent until the prosecutor provides sufficiently overwhelming evidence to prove beyond a reasonable doubt that the defendant is guilty. Notice that the burden of proof is on the prosecution. The defense does not have to prove innocence, right? So the defendant is assumed innocent, presumed as innocent, until proven guilty. So the defense does not have to prove innocence. The defense merely has to show that there's reasonable doubt. The burden is on the prosecution to prove guilt, to provide evidence for that. And a hypothesis test works the same way. So in the justice system analogy, the null hypothesis, H sub 0, is that the defendant is innocent and he did not commit the crime. The defense does not have to prove innocence. They merely have to show that there is reasonable doubt. The alternative hypothesis is known as H sub 1 or H sub A. That is that the defendant is guilty of committing the crime in our analogy. The prosecution has to show that the preponderance of evidence supports their alternative claim of guilt beyond a reasonable doubt. The burden of proof is with the prosecution. So in general hypothesis tests, the null hypothesis is the basic assumption that the sample came from the hypothesized target population. We will assume the null hypothesis is true unless there is very strong evidence to suggest otherwise. So basically, for example, let's say someone claims something and we do a test to see if their claim is right. We're not going to go out and call them a liar unless we have enough evidence to back that up. We're going to assume they're telling the truth unless we've got the evidence to show otherwise. This assumption provides the probability and statistics descriptions necessary to quantify the probability that the sample is from this hypothesized population. The alternative hypothesis is what we're trying to prove. We must have strong evidence to reject the null hypothesis in favor of the alternative hypothesis if we're going to do that. So in a trial, there are two outcomes. The verdict can be either guilty or not guilty. The guilty verdict is like rejecting the null hypothesis in favor of the alternative hypothesis. The prosecution has provided enough evidence to convince the jury that the defendant committed the crime beyond any reasonable doubt. A not guilty verdict is a fail to reject the null hypothesis. The prosecution failed to produce enough evidence to produce beyond a reasonable doubt that the defendant was guilty, so the default assumption of innocent prevails. Now, I may be splitting hairs with what I'm going to say here next, but notice that this is subtly different than a verdict of innocent. The defense does not prove that the defendant is innocent. The prosecution fails to prove that the defendant is guilty, and we fall back on the null hypothesis that they are presumed innocent. So notice that we never really actually prove the null hypothesis in hypothesis testing. What we do is we might fail to prove the alternative hypothesis, so we would fail to reject, but then we just sort of assume that the null hypothesis. So even when we fail to reject the null hypothesis, we're not saying there's not any evidence that the alternative hypothesis might be true. It's just not strong enough that we feel strong enough about making that conclusion. So even when a not guilty verdict is rendered, it might be that the prosecution provided some evidence that looked like, well, maybe they might be guilty, but if they can't provide enough to convince the jury, then they didn't provide enough evidence and a not guilty verdict is returned. Now, when we have a hypothesis test or in a trial, there are two types of outcomes which are correct or good outcomes. The first is what we call a type A correct conclusion. So the one conclusion in the trial is a verdict of guilty when in fact the defendant is actually guilty. So this was going to happen in TV shows where the prosecutor is the star, say, for example, Law and Order. In general hypothesis testing, this is rejecting the null hypothesis in favor of the alternative hypothesis when the alternative hypothesis is actually true. This is called a type A correct conclusion. The other type of thing that would be good would be a type B correct conclusion. If the defendant actually is innocent, then the correct outcome is a verdict of not guilty. And this happens in nearly every episode where the defense attorney is the star, like the old TV shows Perry Mason or Matlock, or maybe a newer one, maybe Bull, where they're defending someone. In general hypothesis testing, this is going to be failing to reject the null hypothesis when the null hypothesis is actually true. This is called a type B correct conclusion. If they're really guilty of the crime, you want them to be convicted. If they're really innocent, you want them to be get a verdict of not guilty. So if the alternative hypothesis is actually true and the null hypothesis is false, you want to reject the null hypothesis. That's a type A correct conclusion. If, on the other hand, the null hypothesis is actually true, you really don't want to reject that. That's a type B correct conclusion. But of course, if you have two types of correct conclusions, there's also two bad outcomes, two types of errors that you could make. The first one is called a type 1 error. If the defendant is actually innocent and the outcome of the trial is a verdict of guilty, then the jury made an error. We don't want that to happen. In general hypothesis testing, this is when we reject the null hypothesis in favor of the alternative hypothesis, when in fact the null hypothesis was actually true. This is called a type 1 error. The other bad thing that could happen is called a type 2 error. This error occurs when a verdict of the trial is not guilty, but the defendant is actually guilty of the crime. In general hypothesis testing, this is when the null hypothesis is not rejected, but the alternative hypothesis is actually true. This is called a type 1 error. In the justice system, in a trial, do we ever have a type 1 error? Do we ever let it convict a guilty, innocent person, but actually convict them? Sure, it happens. Hopefully not very often, but it does happen. Do we ever have the other trial thing that could happen, the other type 2 error? This would be a verdict of the trial turns out to be not guilty, but the guy really did it. Yeah, that happens too. Again, hopefully not much, but it does happen. So that's a type 2 error. Both of these type 1 and type 2 errors could actually happen. And in hypothesis testing, yeah, they really do happen in hypothesis testing. But we'd like the probability of each of these to be small. Okay? Now, let's keep going with this just a minute. So if we reject the null hypothesis in favor of the alternative hypothesis, then we could only have made a type A correct conclusion or a type 1 error. On the other hand, if we fail to reject the null hypothesis, that's the decision we made. If we fail to reject it in favor of the alternative hypothesis, then we can only have made a type B correct conclusion or a type 2 error. Of course, in reality, either the null hypothesis is true or it's false. If the null hypothesis is actually true, we either made a type B correct conclusion if we failed to reject the null hypothesis, or we made a type 1 error if we rejected the null hypothesis in favor of the alternative hypothesis. On the other hand, if the null hypothesis is actually false, then we either made a type A correct conclusion if we rejected the null hypothesis in favor of the alternative hypothesis, or we made a type 2 error if we failed to reject the null hypothesis. Okay, so like in our justice system thing, I mean, the reality is either the guy did the crime or he didn't. If he actually did the crime, then the null hypothesis is false. He's not innocent. So there are only two possible things that could happen. Either we give him a guilty verdict and we made a type A correct conclusion, or we came back with a not guilty, which is a type 2 error. On the other hand, what if the guy's actually innocent? Then the only two things that could actually happen are we made a type B correct conclusion if we came back with a not guilty verdict, a failed to reject the null hypothesis, or we made a type 1 error if we rejected the null hypothesis, that is, we came back with a guilty verdict and we convicted an innocent person. There are conditional probabilities associated with each of these four outcomes. The probability of a type 1 error is alpha. That's the probability that we rejected the null hypothesis given that the null hypothesis is true. Notice that this is the probability of a type 1 error, and it is a conditional probability. We call its value alpha. Probability of a type B correct conclusion is the complementary probability, 1 minus alpha. The probability of a type B correct conclusion is then the probability that we fail to reject the null hypothesis, given that the null hypothesis is actually true. This is also a conditional probability. Notice that the null hypothesis is actually true. The only possible outcomes are type 1 error or type B correct conclusion, so those two probabilities should add up to 1. They're complementary. So the probability of a type B correct conclusion is 1 minus alpha. On the other hand, the probability of a type 2 error we're going to call beta. The probability of a type 2 error is beta. This is also a conditional probability. The probability that we failed to reject the null hypothesis given that the alternative hypothesis is true. So the probability of a type A correct conclusion is the complementary probability 1 minus beta. That is the probability that we reject the null hypothesis in favor of the alternative hypothesis given that the alternative hypothesis is actually true. That's the probability of a type A correct conclusion. It's 1 minus beta. That is also sometimes known as the power of the test. Now I can put these together in a little table here. So if the null hypothesis is true, for example, the defendant is actually innocent, there are only two things that could happen. A type 1 error, that has probability alpha, or type B correct conclusion, that has probability 1 minus alpha. On the other hand, if the alternative hypothesis is true, there's only two things that could possibly happen. The defendant is actually guilty. That has, or the defendant is actually, so if the defendant is actually guilty, if we fail to reject, then a not guilty verdict is returned. That's a type 2 error. That has probability beta. And then this is 1 minus beta for type A correct conclusion. So you can see these. We reject the null hypothesis this row. Fail to reject is the bottom row. This column is null hypothesis true. This is alternative hypothesis true. And I gave the justice system analogy, courtroom analogy stuff there for it. So here is a table, the same table laid out in the same order of the different probabilities. Alpha is a probability of type 1 error, and so forth. So here we see the probabilities associated with each of the four possible outcomes from the previous table, in a table organized in the same way as the previous one. Note that all four of these are conditional probabilities. The probabilities in the first column are conditional probabilities given that the null hypothesis is true. They represent the only two outcomes if the null hypothesis is true. For example, the defendant is innocent. So they must sum to 1. Similarly, the probabilities in the last column also sum to 1. These are the probabilities that the null hypothesis, given that the null hypothesis is false, they are conditional probabilities as well. In reality, either the null hypothesis is true or the null hypothesis is false, although this is not actually known with 100% certainty by the researcher. Now let's think about it a minute. Typically speaking, alpha and beta are kind of working against each other. We would like them both to be small, but I think you can probably see that if we try to make alpha small, we have a tendency to make beta bigger. In other words, if we make it harder to convict an innocent defendant, we're probably going to make it easier for a guilty one to go free. So if we decrease alpha, we're likely to decrease beta, and vice versa. If we make it harder to acquit a guilty person, then we're more likely to convict some innocent people. So alpha and beta kind of work against each other. Ideally, you could make them both small, but in reality, they sometimes are tugging against each other. So which one is worse, a type 1 error or type 2 error? What do you think in terms of the justice system? Is it worse to convict some innocent people, or is it worse to let some guilty people go free? Well, that's kind of a matter of personal preference. You may have different answers on that, but a lot of people in the American justice system would have the basic premise that it's better to let a guilty person go free than to convict an innocent person. So more attention is placing on making alpha small. And it's basically the same way in hypothesis testing. What we end up doing is we decide on an acceptable level of alpha and then use our knowledge of sampling distributions and our knowledge of the distribution that's there to determine a threshold beyond which we have sufficient evidence to reject the null hypothesis in favor of the alternative hypothesis based on that value of alpha. So note that alpha can be any small value, but it's very typical to choose 0.1, 0.05, or 0.01, or in other words, 10%, 5%, or 1% for alpha. These are sort of the usual suspects. Okay? This choice is made based upon how comfortable we are with making a type 1 error. So in some sense, it's somewhat subjective. These are not the only values of alpha. We could just as easily use 2% or 20% or 15%, but these are the ones that are most typically used. Sometimes it may depend on the context. For example, in a manufacturing context, we might be okay with alpha of 0.1 or maybe even 0.2 might be okay. Whereas in a drug test, we might want a very small alpha, like maybe only 1%. Sometimes we have industry standards that sort of determine these for us. So, for example, I've published some papers in mathematics education. I've actually published some papers with a biology colleague. In both cases, the standard for that journal or the standard for that discipline was an alpha level of 5%. So that's what we went with. And that was a pretty typical value. So I would say probably 5% is probably the most common value, but it kind of depends on what you're dealing with. But in any event, that value has to be either chosen or it may be given to you in the problem. So now that we've kind of gone over the basic concept of it, over the next video or two, we're going to learn how to develop the techniques for hypothesis tests, and then we'll get into some examples.